The concept of energy is woven into the fabric of daily conversation, from the fuel powering a morning commute to the electricity illuminating a city at night. Yet, beneath this commonplace terminology lies a profound and often misunderstood principle of the universe. It is not a tangible substance, nor a force that depletes like a finite resource. At its core, energy is a masterful numerical constant, an immutable quantity preserved through every transformation nature performs. This is not merely a scientific concept, but a fundamental statement about how the universe operates, a relentless bookkeeping that governs everything from the swing of a child in a park to the nuclear fusion burning within stars. To grasp this elusive idea, one must first abandon the notion of energy as a thing. It is more akin to an ingenious accounting system. Imagine a meticulous archivist tasked with tracking the entire inventory of a vast, chaotic toy warehouse. The toys, balls, trucks, building blocks are constantly moved, stacked, hidden in cupboards, or even disassembled. The archivist never sees the total inventory at once. Instead, they devise a system of indicators. The weight of a sealed box increases when toys are inside. The water level in a decorative fountain rises slightly if a ball is submerged. The potential energy of a wind-up toy on a high shelf is noted. By combining these disparate measurements, weight, volume, height, into a single, clever formula, the archivist can always arrive at the same total number, regardless of the warehouse's apparent disorder. The individual toys fade from the primary calculation. What remains constant is the derived number. Energy operates on this grand cosmic scale. We do not observe pure energy. We observe its manifestations, motion, heat, height, light, and through a precise mathematical ledger, we find the sum is always conserved in a closed system. This principle of conservation is the bedrock of physics. When a car accelerates, it is not using up energy in a destructive sense. The chemical energy locked in the molecular bonds of gasoline is transformed. Through combustion, it becomes intense thermal energy, heat, which expands gases to create mechanical energy in the pistons, which becomes kinetic energy in the moving car. Concurrently, portions are converted into sound energy from the engine, electrical energy for the dashboard, and wasted thermal energy dissipated into the air via the radiator. If one could magically capture every joule of energy, the car's motion, the heated exhaust, the sound waves, the friction in the tires, the total would exactly equal the chemical energy initially present in the fuel, plus the oxygen used from the air. Nothing is lost. Everything is transformed and redistributed. The various forms this constant number assumes are the currencies in nature's economy. Gravitational potential energy is stored by virtue of position. A boulder perched on a cliff edge holds more than the same boulder at the base, representing the work it could do in falling. Kinetic energy is the energy of motion. Crucially, it scales with the square of velocity. A car traveling at 60 miles per hour does not have twice, but 4 times the kinetic energy of one moving at 30 miles per hour. This quadratic relationship explains why high-speed collisions are catastrophically more destructive and why stopping distances increase dramatically with speed. Thermal energy is essentially microscopic kinetic energy, the frantic, random jostling of atoms and molecules. Rubbing hands together converts macroscopic motion into this microscopic agitation, generating warmth. Chemical energy, stored in the bonds of molecules in batteries, food, and fuel, is released during reactions. Radiant energy, like sunlight and radio waves, travels across the vacuum of space. Even mass itself is a concentrated form of energy, as revealed by Einstein's famous equation, which states that energy equals mass multiplied by the speed of light squared, a relationship harnessed in both nuclear power and nuclear decay. The constancy of energy reveals itself elegantly in simple systems. Consider a pendulum. At the highest point of its arc, it is momentarily still, possessing maximum gravitational potential energy. As it descends, this converts into kinetic energy, reaching a maximum at the lowest point. Then, the kinetic energy is converted back into potential energy as it rises to nearly the same height on the opposite side. In an ideal, frictionless world, this exchange would continue perpetually. The gradual stopping observed in reality is not due to energy disappearance, but to its leakage into other forms, primarily heat through air resistance and friction at the pivot. The total energy, if all forms including this subtle heat were counted, remains unchanged. Why does the universe obey this strict accounting rule? The answer lies in a profound connection between conservation laws and the symmetries of nature. The conservation of energy is fundamentally linked to the fact that the laws of physics do not change from one moment to the next, the symmetry of time. If an experiment performed today yields the same result as the same experiment performed tomorrow, then energy must be conserved. This is not a human invention, but a discovery of a deep structural feature of reality. Similarly, the conservation of momentum is linked to the uniformity of space. The laws of physics are the same everywhere. And the conservation of angular momentum is linked to the isotropy of space. The laws are the same in every direction. This leads to an even more profound framework for understanding motion, the principle of least action. Nature, it seems, chooses the path between 2 points that minimizes, or more precisely, makes stationary, a quantity called action. Action is a measure that combines kinetic and potential energy over the entire duration of a path. One can imagine a particle testing every conceivable, even bizarre, route between a start and finish. The overwhelming majority of these paths cancel each other out in the underlying quantum mechanical description. The path that survives the one we observe in the classical world is the one for which the total action is at an extremum, usually a minimum. This principle elegantly explains why light bends when entering water, taking the path of least time, a related concept, why planets orbit in ellipses, and why a thrown ball follows a parabolic arc. It is a unifying principle that reveals the economy of nature, and from this principle, the conservation of energy naturally emerges. From the steam engines of the Industrial Revolution to the quantum field theories of the modern age, the search for perpetual motion, machines, devices that create energy from nothing has universally failed. Every clever machine, whether a system of levers, pulleys, or inclined planes, ultimately reveals the trade-off inherent in energy transformation. A pulley system may allow a person to lift a heavy weight with less force, but that person must pull the rope over a much longer distance. The product of force and distance, the work done, and thus the energy transferred, remains constant. Any machine claiming to output more energy than it consumes inevitably overlooks a hidden input or a dissipative loss, reaffirming the inviolable conservation law. In conclusion, energy is not a substance that is spent, but a numerical truth that is preserved. It is the universe's ultimate ledger, a constant sum that wears countless disguises. To say a nation needs more energy is, in the strictest physical sense, a misstatement. What is needed are fresh, high-quality sources of energy that can be transformed into useful work before inevitably degrading into dispersed heat. This understanding shifts one's perspective from seeing processes as consumers of a dwindling resource to seeing them as orchestrators of an eternal transformation. The wonder lies not in grasping what energy is in a material sense, but in appreciating the sublime, unwavering constancy of its quantity, a steadfast rule that allows the cosmos to dance in an endless, balanced exchange of form. It is a concept that humbles and empowers, revealing that within every change, from the mundane to the cosmic, there is an unchanging number, whispering the deep-seated symmetries of reality itself.